All right, welcome back to nonlinear finite element analysis. For this video, I want to very briefly recap the deformation gradient, and then we're gonna go into some decompositions that appear a lot that we should talk about. But the first thing is remember that we have some body in the reference configuration. We call that B naught, and that one is in the space in the Euclidean space with the standard basis E1, E2, E3 with Cartesian coordinates, and then we're going to label the points in that body with this capital X vector. So we have capital X is a member of this body, which is a subset of R n, where n can be 2 or 3 depending if we are in 1 or in 2 or 3 dimensions. Typically, I guess it could be 1 dimension, but we're not really doing 1 dimension. So with the deformation, which we call a deformation map phi, we are defining a deformed configuration, and we call that usually B without the subscript. So this is called the deformed configuration as opposed to the reference configuration. And in that, we have points that were originally at X get mapped to points that are in little x. So that's what this map is doing. This map phi maps points from the reference to the deformed configuration. And then another way of putting this was that little vectors x are equal to this map phi of the other vectors x, and this is a vector as well. So it's a vector valued function of a vector input. That was the deformation map, and you should think of this as the motion. So this is the deformation map. Or motion if it depends on time, which I'm skipping right now. And then what we said though is that the most important object in the for the sake of finite elements is not really the motion, but actually the local deformation. So what we said is that associated with this point x, there's a little cube, which we call dv naught, a differential volume element, and that one gets distorted with this map. So a little region around x gets mapped to a little region around little x, and that relationship between the volume, the differential volume dv naught and the differential volume dv, that one is given by the deformation gradient f. So that was the main thing of the previous lecture, is the deformation gradient f, which is, I'm gonna get confused with all the colors, but it's the partial derivative of little x with respect to, I'm gonna stop using colors, with respect to big X, right? So it's a derivative of a vector field with respect to another vector field. So this will be a second order tensor. So remember all the other ones. So X, capital X and lowercase x, those are vector fields, and this one is a second order tensor. And as I said, this deformation gradient has the information about how the neighborhood of x, this cube that I drew here, gets mapped to this other cube in the neighborhood of lowercase x. We said that in components, in this basis, Fij equals the partial derivative of little xi with respect to capital Xj, right? As long as the choice of basis is clear, then this is well defined, and we're not gonna really go into the details of the different bases that you can use. I'm just gonna keep the same basis for the I think for most of the class. And maybe towards the end we'll try to do something fancy with different bases, but for now let's just keep the standard Cartesian basis for both the reference and deformed configuration. So that's the key object in the solid mechanics, because it carries the information of the local deformation. And we said that there's basically three types of things that we can ask from the deformation gradient. We said that we can get changes in length, and this is because what we said is that if we have a little vector, I'm gonna use yet a different color, but at this point, capital X, let me draw some vector and let me call that A naught. Well, that vector gets mapped when I apply the deformation. That vector gets mapped to some other vector A, and that map is given by applying F to the original vector A naught. So we are applying this second order tensor to the vector, we get back a vector, and that vector is going to be probably rotated and stretched. And so based on the length, so this vector is probably rotated with respect to A naught and also stretched or compressed. So we can use basically the length of A and the length of A0 to get changes in length. So we could calculate this, and we can compare against the length of the original vector A naught. So that's one of the things that we can do with the deformation gradient, changes in length. Then the other one is changes in area. And for that, what I illustrated last time was that instead of drawing a little cube, what you can say is, let's say that at this point, capital X, I draw a sphere. And that sphere gets mapped to some sort of ellipsoid in the deformed configuration. Some 3D ellipsoid in the deformed configuration. And then what I'm gonna do is I'm gonna pick some normal at this point X, and that normal defines basically this slice of the sphere. When I apply the F to that normal, I'm gonna end up with another vector which is not necessarily unit length. So let's say that this original normal is unit length. I'm gonna end up with another normal that is not necessarily unit length, and that defines this other plane, right? And then what I said was that let's call this dA naught, and let's call this dA. You can do it in such a way. If it's a unit sphere, then dA naught is not 1, but you could scale your sphere so that the dA naught, for example, is 1. But what matters here is that the rate of the change in area is going to be given by J F minus transpose times N, where J equals the determinant of F and N is a unit normal. In this case, for N, I do need this to be a unit normal. Unit normal in the reference configuration. So basically, F tells me how vectors get mapped. It tells me how, if I define a normal which defines a cross-section of a neighborhood near capital X, it will tell me how much that area gets changed. And finally, I can get changes in volume. And you can keep the same idea of having the two ellipsoids, this ellipsoid or cubes, that's the same. So this sphere here has certain volume dV naught, and then that gets mapped, I should put here, by F. There's the F map, and then we have the ellipsoid, right? And that one has volume dV, and dV equals J dV naught, where J is the determinant of F. So that gives me the volume change. So that's it for F, and I just wanted to have a brief recap of the three things, and that's gonna come up in your homework. Now, the other thing that I defined after that, and again, just quick recap, is what extra with respect to F. So what are other things that you're maybe more familiar with, such as strains? And so what we said is the first define these two tensors that I first introduce this C, which was F transpose F, and I call this the Right-Cauchy-Green deformation tensor. And then I also define, based on this, I define this tensor E as 1/2 of C minus the identity, and I call this the Green-Lagrange strain tensor. And then I also define this B, FF transpose. Hopefully my F's are not confused with E's, and I call this the left Cauchy-Green deformation tensor. And I define this little e 1/2 B inverse minus I minus B inverse, sorry. So identity minus B inverse, and I called this the Euler-Almanzi strain tensor. And these are the strain metrics for large deformation. So typically, I would say the most commonly used ones are going to be C and B. And you can think of C and B as sort of stretches. So C has information about the stretches. It seems like it's very related to C, and actually we'll show that that's the goal actually of this video. I know I'm taking a detour talking about all other things that I talked about last time, but I think it's important to reinforce some of the basic ideas about reference configuration, deform configuration, deformation map, deformation gradient, changes in length, area, and volume, and then right Cauchy-Green deformation tensor, left Cauchy-Green deformation tensor, and the strains. And if you notice, again, now here, I don't think I emphasized this last time, but I use typically capital case tensors for, these are all second order tensors, but I use capital case for things that I will refer to as being in the reference configuration, whereas I use lowercase tensors for things that are associated more directly with the deformed configuration. And part of your homework will go into this, trying to get a little bit more intuition of why do I say that these things are with respect to the reference configuration. So these are tensors associated with the reference configuration. And these are tensors associated with the deformed configuration. And again, that will become clearer later on. But just as I guess a prelude to that, notice how we can parameterize things with respect to this capital X or this lowercase x vector. So we can define vector fields and scalar fields and tensor fields that are parameterized naturally in terms of these capital X coordinates or in terms of these lowercase vectors. So depending on that, is that we'll have things that are more naturally associated with the reference configuration or more naturally associated with the deformed configuration. So that's why I mean by, they measure the same deformation in the end, right? But if they are more natural appearing with respect to this capital X, then they're going to be associated with the reference configuration, whereas if they appear or can be expressed with respect to the lowercase x, then they are going to be associated with the deformed configuration. And again, that will become a little bit clearer as you do some examples. So the first thing that I want to introduce here, as the title suggests, is the polar decomposition, and that will explain a little bit what's happening with this C and B. Why are they so important? So let me put here the polar decomposition. And that just means that F we can split into different tensors. You have probably done this when you were doing linear algebra. You can split a matrix in terms of, for example, the QR decomposition and other types of, which is basically what we're doing now. And what other, I guess you can do the diagonalize tensor, the Cholesky decomposition. There's a bunch of decompositions. Some of them are only applicable to matrices with certain properties, or in this case, tensors with certain properties. And C and B have, these certain properties that are useful, and they will be related to this polar decomposition. So first thing would be F can be split into a rotation and a stretch tensor. So this is called a stretch tensor, and this is a rotation. So this is a symmetric positive definite tensor, and this is just an orthogonal tensor, a rotation. And then another way of writing this would be, a different version of the polar decomposition is to first have a rotation and then have a stretch. So the same rotation, this is same rotation, but two different stretch tensors, the right and the left stretch tensor. And what does this mean? It means that if you remember F, F is doing is, I'm going to do it with a 2D version of F. If we have at point X, capital X, we have a unit square. And then we have at lowercase x, we have our deformed square. Well, it's no longer a square, but it's deformed. And then how do we get from here to here? Obviously, F is what takes us between these two little quadrilaterals, but there's different ways of getting there. One way of getting there would be to first stretch this square that we have right here, and then rotate it. So that would be like this. Or we can, the opposite way would be to first rotate this and then stretch it. That's just basically what the polar decomposition means. So there's some rotation involved. You can you can first stretch a cube and then rotate it, so just you get this final quadrilateral, or you can first rotate it and then stretch it, and you will get to the same place. So that is the polar decomposition. Now, how do you actually compute the polar decomposition? Well, you actually do it with C or B. That's how you do the polar decomposition. Why? Because this rotation is an orthogonal tensor, so that means that its transpose is its inverse. So this is one thing, but how do you get it? How do you compute it? Well, based on the fact that if you do C, which is F transpose F, that would be U transpose rotation U. And this is the identity because this is a rotation, so it's a proper orthogonal tensor. So we have C equals U transpose U. And U is symmetric, so U is symmetric. So C equals U square. And then similarly, you can show that V equals V square. And so if you take the square root of C, you will get to U, or if you take the square root of B, you would get to V. Now, that maybe didn't solve the problem, right? I said, how do you compute this polar decomposition? This, rotation times symmetric positive definite tensor, or symmetric positive definite tensor times rotation tensor, and I was claiming that you could do it with C or B, but I have a square, and so if I want U, I would have to take the square root of C, which doesn't seem possible. How do I take the square root of a tensor? It doesn't seem that nice. But here's where the other decomposition that's in the title of this lecture becomes important, which is the spectral decomposition. And that one is, so C or V or B are symmetric positive definite tensors. So C and B are symmetric positive definite. And what you had to do in the homework was to find the eigenvalues and eigenvectors of this type of tensors. And when you have a symmetric tensor, so symmetric tensors means that you can always pick the eigenvectors to form an orthonormal basis. So the eigenvalues of C would be such that if you apply C to some vector, unit vector n, you're gonna get, well, I'm gonna do this, and I no sum. So in this case, no summation convention, but I have 3 of these, so I equals 1, 2, or 3. Right, so these are the 3 eigenvalues and eigenvectors of C. And because it's symmetric, I can, and I'm gonna do this, because it's symmetric, I can choose the eigenvectors to be orthonormal to each other. And then because it's a positive definite tensor, I can pick the eigenvalues I'm just gonna call them square eigenvalues. But that's fine because I know that all the eigenvalues are positive, so I can just have, lambda square. That's just, yeah, I just choose to do that because that guarantees, that already reflects that they are positive, right? And the spectral decomposition is that I can write C actually as the sum over I from 1 to 3 of the eigenvalues, which I just called lambda square. It's not the square of the eigenvalues I called lambda square. Hopefully that makes sense. Ni, dyadic Ni. Again, no summation convention. There is a sum, so no summation convention. Explicit sum. And this is because there's the reason why there's no summation convention here is because there's 3 i's, so I cannot assume that they are being added. The summation convention only works when you have only 2 repeated indices. The reason why here it also doesn't work is because on the left side I have 1 I, but on the right side I have 2 i's. So then again, there's no match between free indices and dummy indices. So that's why I have no sum here, and that's why I have no explicit, no summation convention. I actually have to write the sum. So what this means is that if I can find the eigenvalues and the eigenvectors of the tensor C, then I can write it as this very, very elegant sum of the eigenvalues times eigenvector dyadic eigenvector, where the eigenvectors I can choose to be an orthonormal basis. So that's something beautiful that you should have done for your homework. And then analogously, you can find that B you can express also as the sum from 1 to 3 of lambda I square Ni dyadic Ni. And there is obviously some relationship between the capital N and the lowercase n, and that's going to be for your homework. But I can use, because B is also a symmetric positive definite tensor, I can also decompose it in the same way, right? And I don't know if I asked this, but I'm just going to say it right now. The eigenvalues are the same, so eigenvalues of, I think I probably said this, eigenvalues of C and B are the same. But the eigenvectors are not. Are not the same, but are related. And it's very simple, but I just want you to tell me what's the relationship between the eigenvectors of C and the eigenvectors of B. Anyway, so this computing the spectral decomposition actually gives you a way of computing the polar decomposition. So I'm gonna look back here. So if you compute the spectral decomposition, then you can write U as the sum from 1 to 3 of Li Ni dyadic Ni, and B sum from 1 to 3 of Li Ni dyadic Ni. And this is also why I named this square, because as I said, this one is a symmetric positive definite tensor. Both C and B are symmetric positive definite tensors, and so just by convenience, because I know that I have to guarantee that the eigen values are positive, I just named them with a square. But these are the eigenvalues of C. But if I take the square root of those eigenvalues, then I get the eigenvalues of U and B, and that's actually how I can compute this square root. So here it was like, I need to take the square root of C, how do I do that? Or I need to take the square root of B, how do I do that? Well, you can do it with the spectral decomposition of C and B. Alright, so I still will have one extra topic that I want to cover here, but let me just recap one sec. So I have F, but as I said, F we don't really use directly. The terms that are used are strains or deformation tensors, and particularly this C or this B, which are the left and the right and the left Cauchy-Green deformation tensors, and they are obtained by either F transpose F or FF transpose, and they have corresponding strains associated with them. And there is a reason why it's C and B that are used. And that is because F has a little bit more information than what we want. I think I mentioned this last time. So F has all this information about the changes in length, changes in area, changes in volume, but it also has information about changes in orientation, for example. And this I was saying here, this is clear when you look at the changes in vectors. So if you apply F to A0, then it gets mapped to A, but that involves both some stretching but also some rotation of A0. And then not all the deformation actually it's involved in having strain energy or causing stress. So actually local rotations are not associated with actual deformation of or stretch. And C and B get rid of that rotation. So when you look at the polar decomposition, like we said, the polar decomposition basically tells you that for a given deformation, there's part of the deformation that is just rotating this little piece of differential volume or differential area, and another part that is actually stretching it. And in order to compute stresses, we're not really interested at the part that is rotating the little square that we have here. We're only really interested in the part that is actually deforming it. And C and B get rid of that because the rotation is an orthogonal tensor, so its transpose, it's inverse. Then when you do either F transpose F or FF transpose, you get rid of the rotation and you keep only this U, this stretch tensor, or this V. And so that's why we use C and B and not F, typically, because we want to get rid of the rotations. And yeah, so and typically you would only use C and B, and then in some cases you might have to express things in terms of the eigenvalues, so principal eigenvalues and principal directions or the eigenvectors of C and B, and then that's where the spectral decomposition comes from. And it comes about because C and B are special. They are symmetric positive definite, which means that the eigenvectors can be chosen to be an orthonormal basis, and so it allows for a really neat representation of the tensor in terms of the basis of the new basis defined by the eigenvectors. So that's about it for that decomposition. And then the last decomposition that I want to introduce is this notion of isochoric part of F. And this is associated with the idea that materials have different behavior when we are talking about changes in volume or hydrostatic stresses or dilational deformation. So basically things that do not really distort the material, but they just want to expand it or contract it. And so those are volumetric changes. So the deformation we might be interested in, deformations that are associated with volume changes. And deformations that are associated with distortion. So again, you can think of, I have my little square in big X, and then that gets mapped to some position little x, right? And the map between these two is F, right? But clearly there's two things that are going on. One is that this square might be a little bit bigger than the original square, and the other one is that there might be some distortion of the square, right? So these are the two types of deformations that I want. And actually the material might have different resistance to things that just wants to compress the material or change its volume, and things that want to distort the material. So because of that, we want to split the deformation gradient into these two portions. So the one that captures the volume change, it's going to be basically just J to the 1/3 identity. So only basically volume changes, where J is the determinant of F. And the distortion is going to be the other part. So what do you need to get back the total F? That's going to be j to the minus 1/3 of f. Right, so that if we scale f by j to the minus 1/3, now determinant of, and you can think of this as basically all I'm saying is f equals j to the 1/3 I times j to the minus 1/3 f, which is trivial, right? And I'm just saying like this is gonna be j to the 1/3, and I'm having a special name for this j to the minus 1/3 f. I'm gonna call it f hat, and this one is called the isochoric part, or volume preserving, basically. Also distortional component of f, right? Because the determinant, and that's because the determinant of f hat equals 1. So all the, and remember that the determinant is the volume change. So all the volume change is basically here, right? So f hat doesn't have volume change, so it only has the distortional component. So this is very, very typically used. So instead of using, and similarly, not just f hat, but actually from f hat we can compute this c hat, which is just f hat transpose f, right, which is j to the minus 2/3 of c, of the standard c, right? And this one is also the isochoric Ricochet-Green deformation tensor. And again, all that we are doing is we're splitting the deformation into a part that preserves volume and just cares about the distortion, and a part that worries about volume changes. And we're not gonna really get back to this until later when we do hyperelastic materials, but there's a bunch of strength energy functions that are defined in terms of this c hat. So you can, I'm just going to introduce many times behavior of material split into a part that is a function of c hat and a part that is a function of j. So a part that deals with just distortions, and a part that deals with volume changes. All right, so that's all that I wanted to